Okay, so now let's talk about hydration and hydroboration reactions. Remember when we were talking about alkenes, those were ways to form alcohols. We're going to see something similar here. Let's take these one by one. We'll talk about hydration first. So we're going to again have like an acid catalyzed hydration. So that's what our our sulfuric acid and water are doing for us. With alkynes, you always have that mercury catalyst, right? So we saw mercury catalyzed hydrations with alkenes, but we also saw examples of just acid catalyzed hydrations. Here it's always going to be mercury catalyzed hydrations. And just like we saw with our previous hydration reactions, you're going to get substitution on that more highly substituted carbons. So this is going to be our Markovnikov hydration. Okay, so we're going to form something like this. All right, this is called an enol. So let's pick this name apart real quick. En because it's got this double bond, and ol because of the alcohol group. So an enol is when you have a double bond that's directly adjacent to an alcohol. Okay, or that alcohol group is on that sp2 hybridized carbon. Okay, so this is what we would expect just based on what we saw before, hydration of that more highly substituted carbon. It turns out that this enol is not isolated, and it will quickly rearrange itself to form a ketone. Okay, these have the same molecular formula. Okay, this enol and this ketone. The big difference is that double bond has changed places, as well as this hydrogen right here in our ketone has moved to this carbon here, right? They have the same molecular formula. It's just an internal rearrangement that occurs. It's called a tautomerization. Okay, so this tautomerization is going to be a big part of this chapter. Again, you do have substitution on that more highly substituted, you do have addition rather to that more highly substituted carbon, but then you have this internal rearrangement that takes place. And so instead of getting an enol, you get a ketone. Enols are actually just non-isolatable, they're not stable. So let's see what the heck happens here. So first of all, and this isn't really a reaction mechanism that I expect you guys to have memorized. Number one, because it's kind of not that well understood. And number two, you can find many different textbooks that have different reaction mechanisms. Your textbook in particular is different from what I'm going to teach here. And let's not get bogged down on the differences, but bottom line is to say that it's still a little murky as to what occurs. But what's clear is that we have this triple bond playing the role of a nucleophile. And then just like we saw with our other mercury catalyzed reactions, we actually have the formation of a cyclic mercurium, I think, ion. Okay, that means that we're going to have an anti-addition of water to the other side of this bond, to the other side of this complex here, right? So this is anti. Turns out that luckily, that because of this tautomerization, that anti-addition doesn't matter, meaning like you don't have to commit that to memory too hard because it's not going to play a role in the stereochemistry of our product. Yeah. But just to sort of show what happens here, you then have deprotonation to form your alcohol group. Whoops. To form your alcohol group. Messed that up tonight. And then you still have that mercury group there. That will then, in a second step, be replaced by a hydrogen. Okay, so this is the formation of your enol. Again, not this portion of the mechanism is not what I expect you to know. And again, I don't know that anybody really knows. Okay, this tautomerization mechanism is important. That is how we go from the enol to the ketone. This I expect you to know. Okay, and this is actually going to be, first we're going to learn about an acid catalyzed enol, keto to enol tautomerization. Maybe I spelled it wrong before. Anyways, that's what this word is, tautomerization. And again, it just means like this internal rearrangement that's going on. And it's going to be acid catalyzed. Okay, so we're going to have an acid that's going to be important to like edge this thing along, but it's not going to be consumed in the reaction. So what's the first step here? We have our enol, we have this acid. Well, what do we know about double bonds in acid? Double bonds can play, pi bonds can play the role of a base. And so that's exactly what happens here. We have protonation, or rather proton transfer that occurs, and that creates this carbocation. Okay? This carbocation right here can undergo resonance, right? And in particular, will create this, whoops. It'll undergo resonance in such a way where this pair of electrons comes down, and so that places the positive charge on that oxygen. And this is actually the more stable of those two resonance contributors. Why is that? Right, remember that positive charges generally want to sit on the less electronegative atom. Right, so maybe it wouldn't be obvious that the oxygen is more happy with the positive charge. The real reason is that carbocations have incomplete octets. So when oxygen donates that pair of electrons, yes, it has to bear that positive charge, but everybody on this resonance structure has a complete octet. So this is our more stable resonance structure. And then what happens is this water is going to reach over, reforming our acid catalyst and deprotonate that alcohol, oxygen, leaving us with a ketone. So this is an acid catalyzed keto to enol, right? So ketone, keto being for ketone, enol being for enol, tautomerization. Okay? So just to summarize here, we're talking about the mechanism. For this portion, the mercury catalyzed hydration, you don't need to know the mechanism. For this portion, the tautomerization, you do need to know the mechanism. Put it down here just to make it super duper clear, right? That tautomerization is an important thing to know. Regioselectivity. I can't spell. Regioselectivity. Yes, this is really important. You have a Markovnikov addition, meaning that that hydroxyl group is going to go on the more highly substituted carbon. And now in terms of stereoselectivity, if it stopped at this enol step, we would have to know that this was an anti-addition, but because it rearranges, it tautomerizes, we actually don't have to worry about any stereoselectivity. There's no stereochemistry to a ketone. Right, so now let's talk about hydroboration, right? So if we remember before, this means, well, let's just look. So before we were using something like BH3, notice that this is R2BH. So like instead of being BH3, it's got the bromine, but now there's two other groups. We'll see that these have to be like big bulky groups. We'll talk about why that is in a second, but they're gonna play very, very similar roles. Well, so what was our hydroboronation doing for us when we were talking about alkenes? You guys remember? Just like our hydration reaction, it was creating alcohol groups. But the big deal, the shtick with the hydroboration is that it was an anti-Markovnikov addition, right? So here we're going to see the exact same thing for our alkynes. We're going to produce the Markovnikov product, meaning that we instead get substitution of that hydroxyl group on that less highly substituted carbon. But just like we saw with our hydration reaction, this is again an enol, but it is not going to be stable. It is instead going to rearrange itself or tautomerize in order to form a new carbonyl group. This is actually, instead of a ketone, this is an aldehyde, right? And it's an aldehyde because it's on the very end. Now we have a new tautomerization mechanism. Okay, so this is going to instead be a base catalyzed tautomerization. So again, enols not terribly stable. They will always want to rearrange themselves. They can do so either in acidic conditions or basic conditions, and the mechanism is just a little bit different. So in a basic conditions, what happens, the first step is instead deprotonation of that alcohol group. Okay, this will form, now we'll have a negative charge on our oxygen. This can again undergo resonance. This guy right here, where you have this negative charge, both of these combined, remember how resonance works, right? We're not talking about this is one structure and this is another structure. They're constantly in resonance with one another. So they're both true at the same time. This is what we call an enolate ion. It'll play a more major role in the second semester, but good to know. Again, this resonance will occur. This is actually the less stable of the two, but nonetheless is going to be an important player. It does mean that the base catalyzed tautomerization is a little bit slower than the acid catalyzed, right? Because the key player here is actually the less stable of the two resonance structures. And I guess, let me just show you how we got this resonance structure. This pair of electrons on the down, and so we formed a carbanion. We know it's the less stable of the two because the more electronegative atom would like to hold that negative charge. Nonetheless, the key player is this guy here. What's going to happen is the carbanion is going to play the role of a base now and reach over and grab a proton from water. Notice that I'm reforming my hydroxide catalyst here, and now I end with an aldehyde. Okay. All right, so why can't we use BH3? It's because BH3 is really small, and so what would end up happening is it would associate with our alkyne twice. First to form an alkene, but then again, just like we saw with reactions with alkynes. And we don't want that to happen. That's not going to be any good. So what instead we're going to use is a something similar, but it's got big, bulky groups and only one hydrogen, right? So this is R2BH is going to represent something like this guy here. This is another one, even, great, right? So now you have this big bulky ring system. The point being is that these R's represent big groups, and that prevents any undesired products from forming. Very similar to the hydroboration oxidation of alkenes, but again with alkynes, that BH3 is going to look a little bit different. Instead of using BH3, we use this guy. Okay, everything else is the same though. So I don't really want you, I don't know. I don't want you guys to memorize all the different types. I think more importantly is just recognizing that. Okay. Diisoamylborane, sure. If you get that, or the BBN rather, sorry, great. I think more importantly is just recognizing this here, right? That R2 stands for a big bulky group. And what is this going to produce? An aldehyde, right? So again, we're going to form that enol. We're going to get, well, I guess first we're going to get substitution on that less highly substituted carbon. So we're going to form a terminal enol, but that's going to rearrange itself and form an aldehyde. Okay, so that means that we have, with our different hydration reactions, we have different regiochemical control, right? If we want, given a terminal alkyne, if we want a ketone, then we need the Markovnikov addition. And so we're going to use acid, water, and this mercury sulfate catalyst, right? This will give us our Markovnikov addition. I guess we can color code here. And that will give us a ketone, right? Because that carbonyl group will be an internal carbonyl group. Or we can get the anti-Markovnikov hydration, which will again substitute on that less highly substitute carbon, form that terminal enol, and then that will rearrange itself to give us an aldehyde. Okay, notice that we're not going to get an enol. It's just not going to happen, right? So we are not going to form alcohol groups from our alkenes, or I'm sorry, from our alkynes. We're instead forming carbon-oxygen double bonds or carbonyl bonds, either ketones or aldehydes, depending on whether they're internal or terminal. All right, so then just to summarize what we learned, in terms of mechanism. So again, for both of these hydrations, you don't need to know the mechanism of what's happening with the borane. What you need to know is the tautomerization, right? So that base catalyzed tautomerization, that I do expect you to know. Should really know whether it's an irony, but I really don't. Regioselectivity. So yes, with our hydration, with the mercury catalyzed, we have the Markovnikov. And with our hydroboration, we have the anti-Markovnikov. Last, stereoselectivity. Fortunately, we don't have to worry about that because there's just not any stereochemistry associated with ketones or aldehydes.